Greetings to you. Today we will discuss about 4 elements, that is aluminum, and, sulphate, cyanide and ammonium. These 4 ions are normally determined in the effluent samples, and we will start with aluminum. Regarding aluminum, I want to tell you that aluminum is a non-essential element for both plants as well as animals, but aluminum is very widely distributed in the nature, in the soil and in the air also. In the air we breathe, there is about 20 to 25 ppm, the parts per billion, ppb level of aluminum in the background. So, aluminum is very widely distributed, therefore, it is important that we have to understand about the toxicity of aluminum. Normally, concentrations greater than 1.5 milligram per liter constitutes a toxicity hazard in the marine environment. That means, in high salt solutions, if the aluminum is more than 1.5 milligram per liter, then it causes toxicity in the marine animals like fish and other things, algae, plant environment as well as animal environment, and even in small rivulets. Normally aluminum precipitates around pH 5 or so, pH 5, 6, more than pH 3 it will start precipitating, and when the water pH is about 5 or 6 or 7, you may not find much dissolved aluminum in that, but you will find that most of the aluminum has been precipitated at the bottom of the rivers and rivulets, and if there is not much force in the water movement, most of the bottom is covered with aluminum hydroxide precipitate. And the pH of the near the bottom of a flowing stream changes quite often depending upon the input, and there are a lot of animals which are floating very near the bottom, protozoa, bacteria and several other things, and many animals are in that area within 2 to 3 millimeter of the bottom, within 2 to 3 millimeter height of the water from the bottom would be exposed to high aluminum concentrations. So, that can become toxic, the aluminum at that level, and then it can cause a disturbance in the natural cycle of the plant and animal life. So, levels below 200 microgram per liter present minimal risk. So, aluminum has been quite practically implicated in Alzheimer's disease. So, normally people who drink from aluminum cans, they are high risk people for Alzheimer's diseases, etc., especially if you are in the habit of drinking Coca-Cola or something from aluminum cans, you should be slightly worried about the dissolved aluminum levels in the human body. So, aluminum levels in brain tissues are suspected to be linked to Alzheimer's disease. So, I will show you the first slide now, that is that contains all the ideas what I have given you, and we normally use aluminum also as a very highly industrial product. Usually aluminum is used in industries for roofing, etc. Aluminum is very common, it is corrosion resistant. Normally it has a coating of aluminum oxide on the surface when exposed to the air, and it provides a very safe environment for the corrosion resistance. So, normally aluminum is also used as for aesthetic purposes, for windows and things like that, and the wasted aluminum vessels are used for cooking, and that also could be one cause for Alzheimer's disease, and therefore, it is important that we determine aluminum in very low levels. So, aluminum is normally determined using areochrome cyanine R. This is a triphenyl methane substance dye, and it has got SO3 Na groups that makes it solubilize it very easily, and then it has got about COH groups and CON groups and CH3 like that, quite possible to complex metals using these links CH3 oxygen, and there is one more here, etc. And the complex structure of the complex you can look up in the standard textbooks. So, to determine aluminum, what we do is normally we go for 1000 ppm stock solution, which is prepared by dissolving 1.758 gram of aluminum sulphate, and working solution should be approximately 100 ppm. Sulfuric acid should be approximately 0.02 normal, and this you can prepare up to 100 ml, and but before you use it should be diluted to 50 ml with deionized water. And then you also need a buffer of sodium acetate acetic acid, that is around pH 4. The buffer concentration should be approximately about 0.3 molar. So, you can prepare the dissolved you can, by dissolving sodium acetate in 50 ml and add a 4 ml of glacial acetic acid, you can make it and then use it. Areochrome cyanine R is available across the shelf. It is a very good dye for clothes also, and you have to dissolve 0.015 gram of areochrome cyanine R in 5 ml of deionized water. So, what we have done is, usually in such aluminum determination there will be a formation of some sort of lake. That means a sort of precipitate may be obtained, and as you know, precipitate is not good for spectrophotometry. So, what we have done is, in this case we are asking you to prepare cetyl trimethyl ammonium bromide, that is CTAB. It is a cationic surfactant. You have to prepare 0.1% of CTAB, that is that will keep the small precipitates particles in solution. So, that is the modification we have done to the standard method, and then the procedure is very simple now. If you have all the reagents, all you got to do is take the standard solutions, aliquot of aluminum in 10 ml standard flask, that is as usual. Then you add 200 microliter of sulfuric acid, 1 ml of working dye, 1 ml of CTAB and 2 ml of buffer, and then you have to add your reagents, the aluminum. You also need the complex gives you an absorbance at 535 nanometer, that is again it is a sort of purple red color. So, recommended sample volume is 1 microliter, 1 milliliter, and the cookbook value for 2 microgram of aluminum in 10 ml, that is 0.2 ppm, should give you an absorbance of about 0.25 plus or minus 0.01 absorbance. So, this is the spectrum of aluminum, that is aluminum and areochrome cyanine R complex. This spectrum has been taken against a blank, because I am showing you only one figure, and against the blank you can see that there is an lambda max around 525 or so, and let us say around 530, 535 you are getting the lambda max, and the calibration curve will show you aluminum areochrome cyanine R complex follows Beer-Lambert's law up to 3.5 micrograms in 10 ml. That is a fantastic improvement over the aqueous extraction procedure, but the linearity is also fairly okay. The least square index R square gives you a value of approximately 0.996, which means that the method is very sensitive and follows a good gives you a good linearity, which means the results will be highly dependable. So, I would also like to add here that the method needs to be standardized every time, because the color is not very stable for long time. So, every time you have to prepare a standard and then do the determination. So, that brings me to the another parameter, that is cyanide. Cyanide is a parameter of importance, and everybody knows that cyanide is a highly poisonous chemical, very difficult to handle. You are not allowed to keep it in the laboratory unless you are trained to handle it, but cyanide has got a very varied uses in our day to day industrial life. We may not be using it much in normal circumstances, but cyanide is a very important plating chemical. So, cyanide people doing plating will employ kilograms of cyanide, and then there is another process that is known as nitriding. Many of the industrial chemicals in metals which are part of the machines, they have to provide very hard surface. So, this hard surface should be a few microns, or maybe 1.5 millimeters or something like that, and that kind of surface is prepared by taking the metal and dipping it in a cyanide solution and then melt the cyanide salt, and keep the cyanide salt melted for about 5 to 6 hours or 10 hours according to the procedure, which imparts hardness to the metal surface, that is known as nitriding. So, the nitrogen combines with the iron particles on the surface, that will give you a nitrided metal surface. So, that is also a very important aspect of industrial life, and I have seen people who use cyanide in kilogram quantities with bare hands. Of course, that is not a very good practice, because any cut in the hand or something like that you are handling, the cyanide, a person may die. And cyanide is, the action of cyanide is known to occur through the replacement of oxygen by cyanide in the hemoglobin. As you know, hemoglobin is a porphyrin like structure with iron at the iron in the center, and then on 4 sides parallel on the same plane nitrogen porphyrin groups are there. On the top there is another nitrogen group bound to a proton, and at the bottom it is a oxygen and carbon dioxide. Oxygen and carbon dioxide, as we breathe in we take up oxygen, and oxygen goes and sits attaches itself to iron, and then as we breathe out, the carbon dioxide will be carbon dioxide will be exited from the same spot. So, carbon dioxide and oxygen normally are exchangeable in a red blood cell in our body. Now, if I have some cyanide in my body, the cyanide will go and attach it at the attach it to iron complex, hemoglobin complex at the bottom where oxygen should have been there, and cyanide attaches itself so strongly that it won't give a chance for oxygen to attach itself. That means cyanide has to go, oxygen has to come in. So, this equilibrium is disturbed. Once it is disturbed, it becomes irreversible and a person will die of asphyxiation. So, the reaction is very fast, and people say that they have not been able to determine the taste of cyanide also, because before it is determined, the person would die. So, cyanide we have to worry about in the environment, because especially from electroplating industries and metal finishing industries. So, the my slide shows you that exactly the same information, that is highly toxic. The BIS prescribes a limit of 0.05 ppm. The following method is applicable to cyanide, that is amenable to chlorination in the absence of interfering substances like thiocyanates. So, the normal method is use chloramine T and barbituric acid, where cyanide will react with chloramine T at pH less than 8 to form cyanogen chloride. This then reacts with pyridine barbituric acid reagent to form a red blue color. The absorbance of the solution at 578 nanometer is usually related to the concentration of cyanide. A very simple and straightforward method. All the reagents are available across the shelf, and this is the chloramine T complex reagent. It is sodium chloramine T and Na plus and chloramine T minus. This chloramine T is nothing but N-chloro 4-methyl benzene sulfonamide, this sodium salt, and this is the structure of barbituric acid, that is NHNH, and pyridine reaction. Pyridine is a very simple chemical just like benzene, where instead of the 6th carbon atom there is only one nitrogen there. So, the reagents, the chloramine T is prepared by dissolving 1 gram of chloramine T. It is available in quite large quantities. It is an industrial chemical also, and you can dissolve it in water, make up to 100 ml. Normally chloramine T solutions are stable for about 1 week. That means every week you have to prepare fresh chloramine T if you want to determine cyanide. So, it is also important that you prepare about sodium hydroxide, 4 gram of sodium hydroxide in deionized water with about 100 ml solution you can prepare, and from this you have to prepare 0.16% of sodium hydroxide again, because normally you can straight away prepare 0.16% sodium hydroxide also, but the procedure according to us, what we feel is 4% sodium hydroxide is quite stable, and the 0.16% you can determine as and when you need it. So, for every experiment you can just do this dilution, and sodium cyanide is the standard chemical. You have to prepare 1000 ppm and dissolve it. Potassium cyanide is available in the market, and you have to dissolve it in 4% of sodium hydroxide solution and dilute to 100 ml. That means the cyanide solution should be in alkaline medium. So, if the cyanide is in acidic medium, it will release hydrogen cyanide gas, and which may cause a problem of toxicity. So, one has to be very careful how you store your cyanide in the laboratory also. So, standard working solution, you can prepare up to 20 ppm, that is no problem, and pyridine barbituric acid reagent you have to prepare separately, taking barbituric acid as well as the pyridine. What you should do is dissolve about 15 gram of barbituric acid in 250 ml conical flask, just add enough deionized water to keep the barbituric acid in solution, that is quite soluble in water. And then you have to add about 75 ml of pyridine, and that you should do in a fume cupboard, because pyridine vapors are also not good for breathing. So, only all these procedures you have to handle in a fume cupboard, and you have to take adequate precautions for preparing the solutions and as well as handling the solutions. So, we can add a little bit of concentrated hydrochloric acid also, and cool to room temperature, dilute to volume, mix and stable, but once you prepare this, it is stable for about 6 months. Then you need to prepare acetic acid state buffer, that is sodium acetate acetic acid. So, you can take trihydrate and mix in the proportions mentioned here, that is 41 gram as well as sodium acetate trihydrate and 50 ml of glacial acetic acid. So, under using these things you can make up to 100 ml and start preparing. The procedure is you take 20 to 100 microliter of 20 ppm standard cyanide in different flasks, and add the sodium hydroxide 0.16% and add about 200 microliter of acetate buffer, 400 microliter of chloramine T, and mix them and let them stand for 2 minutes, then add your 1 ml pyridine barbituric acid solution. So, dilute to the mark, mix and let stand for about 8 minutes. So, you have to measure the absorbance at 578, which means the complex should be somewhat bluish in color. Okay. So, you have to prepare a calibration curve of the absorbance versus concentration of the cyanide, and you can determine the concentration of the sample by referring to the calibration curve as usual. So, there is nothing very specific about it, but one thing you should remember is the color is stable for only about 15 minutes. That means it does not give you, the procedure does not give you enough time to keep the sample and measure at your convenience. It is better you should measure this color within 15 minutes, and the recommended volume is about 1 ml. So, cookbook value for 40 microgram gives you an absorbance of about 0.286 grams, absorbance, not grams. And the cyanide pyridine barbituric acid method shows you a lambda max. Spectrum shows like this, that is the spectrum taken against the blank. So, you can see that it gives a very sharp peak somewhere around 560, 570, which I have mentioned in my previous slide, that is at what is the wavelength, that is 578 nanometers. So, that will give you fairly good sensitivity, and this is the linearity curve for cyanide. Not very good in terms of linearity, because R square value is approximately 0.983, but if you are determining 10 micrograms in 10 ml, that is 1 ppm, 1 ppm should give you an absorbance of about this much. So 0.05 ppm should be able to, you should be able to get about 0.05 absorbance, which should be fairly okay as far as the method is concerned. It should work for most of the industrial applications without any dilution. That is the beauty. So now I will continue explaining about the determination of sulphate. Determination of sulphate is very important. I do not have to mention to you that sulphate is not a pollutant in the normal sense, but sulphate is there everywhere. Just like chloride, sulphate is there in the soil, it is there in the water, it is there in the air we breathe, and most of the automobile exhausts in the environment spew out sulfur dioxide, which gets converted into sulphate in the atmosphere. Whenever there is rain or something like that, the sulphate will combine with some of the metal ions in the air, and then sulphate will rain, forming sulfuric acid also, as well as some other metal salts, and sulphate is implicated in acid rain. So that follows naturally. Therefore, sulphate is there all around us again, and sulphate regarding health concerns, I should tell you that it does not cause you any problem as such, but higher level of sulphates usually end up giving you irritation, because the taste of water is not, does not the taste of water is not good when it contains high levels of sulphate. So, health concerns regarding sulphate in drinking water have been raised because of reports that sometimes diarrhea and dehydration may be associated, but it is not proven yet with the ingestion of water containing high levels of sulphate. As of now, what we would like to remember is more than 200 ppm of sulphate in drinking water is not good. So, whenever you take a water drink water from a bore well, chances are you may have higher levels of sulphate if the water is drawn from about more than 200, 300, 400 feet, then the sulphate will be in higher quantities. So, that is one reason why most of the drinking water has to be monitored for sulphate. So, there is another possibility that the people are sensitive with to sulphate even with small quantities of sulphate with respect to age. It has something to do with the age. Infants are usually very sensitive to sulphate than the adults. So, older children and adults become accustomed to high sulphate levels, but children it is a bit of a problem. So, after a few days of particular concern, there are groups within a population that may be at a greater risk than others. This happens because of the laxative properties of the sulphate. So, an abrupt change from the water what you drink is always could be a cause for indigestion and diarrhea. Now, many people do not recognize it as one of the reasons for sulphate, and it is not so easily detectable nor it is proven, but chances are there. If the water what you are drinking suddenly changes characteristics, you move to some other town, some other place, and then start drinking that water, there will be a problem of this water causing you diarrhea. Sulphate is also not very good with respect to laundry. The industrial municipal water, river waters contain about 60 to 80 ppm of sulphate, and higher than that is not really good. We will continue our discussion of sulphate in the next class.